In this video, we will cover section 2.4, sequences and summations, although we will only focus on sequences because that's all we need for this course. Okay, so by the end of this video, you should be able to define a sequence by a recurrence relation and determine if a given sequence is a solution of a given recurrence relation. We also will look at a couple of methods for solving recurrence relations within this video, but of course we will again apply this in class, as it may be difficult to follow along in this video without some additional actions and additional notations. There are also a variety of applications to finance, population growth, and production, which is why learning about sequences and solving recurrence relations is very important. So this is a particularly useful section to develop your knowledge in order to be able to continue with one of the main course outcomes in defining recurrence relations and solving recurrence relations in general. Okay, so you may know what a sequence is already. Nonetheless, in general, a sequence is an ordered list of elements. So here are some examples. 1, 2, 3, 5, 8 is a finite sequence of elements. 1, 3, 9, 27, 81, which continues this same pattern, which if you may recognize is powers of 3, is an infinite sequence following that pattern. As I mentioned previously, sequences are very important throughout mathematics in solving various recurrence relations, as we'll define later on, apply to a variety of different areas from finance, population growth, and a variety of other areas. Sequences also arise throughout mathematics, computer science, and in many other disciplines ranging from botany to music. So we will introduce the terminology to represent sequences, but we will avoid the sums of the terms in the sequence, although that just means summing each of these terms and evaluating either infinite or finite sums, depending on whether your sequence is infinite or finite. So more formally, a sequence is a function from a subset of the integers, usually either the set of natural numbers, 0, 1, 2, 3, 4, and so on, or the set of positive integers, 1, 2, 3, 4, and so on. So either the integers or natural numbers are the domain of the function, which defines the sequence, and the codomain is any set S where the elements of the sequence take place. So in our previous examples, our elements also fell within the natural numbers and the positive integers, in fact. So a sequence is just a function, but it's a special function defined on a particular domain, either the natural numbers or the positive integers. So normally, we use the following notation to denote sequences. So we use the notation A sub n to be the image of the integer n. So essentially, this A sub n is going to be equal to f sub n, where f is the function which defines the sequence from either the set of natural numbers to the set S or the set of positive integers to the set S. And we will determine in which case we define a sequence according to which domain. So each element an is a term of this sequence. Okay, so let's look at some examples to make this a bit more clear. So to represent a sequence, we can do it in a number of ways, just as we have for functions in the previous section. So one of the common ways is to denote it by a formula. So a sub n is equal to 1 over n. So this is a particular example of a sequence where our domain needs to be the set of positive integers and not the set of natural numbers, specifically because a sub 0 would be undefined. So notice that a sub n, this n corresponds to this n in the formula. So a sub 0 would be 1 divided by 0, which we know is an undefined number. It's essentially infinity. So that's why we need to define this sequence in a set of positive integers and not define it for 0, because a sub 0 is an undefined term using this formula. So another way to represent this sequence is just to list the terms as we saw in the previous examples. So in this case, we list the terms starting from 1. So a sub 1 is 1 divided by 1, which is 1. A sub 2 is 1 over 2, or 1/2. A sub 3 is 1 over 3, or 1/3, and so on. So we get to a sub n equal to 1 over n for every positive integer n. We could also represent a sequence in set builder notation. So if we see these curly brackets around the sequence, this is just saying that we're listing our elements of our sequence within a set. So if our sequence an was going to be defined by the formula 1 over n, we could just take these values and list them in set builder notation with the curly brackets. So these are all common ways to represent sequences, and you will see each of these throughout the textbook and throughout the course.